Hi, everyone. My name is Raquel Urtasun, and I'm the founder and CEO of Wabi. Today, I'm going to be talking about interpretable neuromotion planning. But before we go to this, let's very briefly remind you how a self-driving vehicle actually works, and in particular, its autonomy stack. So the vehicle first senses the environment. This typically is done with LiDAR, cameras, radar, etc. What I'm showing you here is a view from the top where we see the LiDAR point clouds in bird's eye view. The first thing that these vehicles do after sensing the environment is to localize where they are with precision of a few centimeters. Reasons for this is that they want to exploit high definition maps in order to do better perception prediction as well as motion planning. Once localized, the vehicle needs to basically estimate where everybody is around it, as well as predict the trajectory of the actors into the future. And this is important in order to be able to come up with a trajectory for the self-driving vehicle that is safe towards the goal and that is comfortable as well. And this is a task of motion planning. Finally, this is repeated every fraction of a second, and the control system basically makes sure that what the vehicle intended to execute is actually what is executed. The small differences typically arise because of things like friction or not having the right vehicle dynamics. All right, so if you look at the approaches in industry to try to solve self-driving, try to build an autonomous system. So we've seen quite a bit of progress in the past couple of decades, say 2 decades since the DARPA challenge. However, we see really an impasse in the sense that current approaches are not really able to generalize to the distribution of long-tail events that might happen around the world. And one of the main reasons, in my opinion, of this is actually the technology employed. They utilize what I call the traditional engineering approach, which is very reminiscent with what I was talking about before. But it has a few key disadvantages or problems when you actually try to implement this in the real world. So let's review quickly what these are. First is the fact that we have this modularity, right? I was talking about perception, prediction, motion planning. But what happens is that in order to model every one of these these big boxes here, there is actually, if you go inside, there is actually a much more complex system where you have typically hundreds of models, for example, for the perception system. And then what happens is that every one of these models is executed one after another. So if developing silos, right? So for example, you might be a perception engineer. Within perception, you are targeted with developing a tracker for pedestrians. And then you have very little information about really what is the rest of the stack. So it's really, really hard to build a good autonomy system this way. Okay, so this sort of the development of the different things in self-driving typically are done in silos. Right? So think about trying to build a puzzle where instead of cutting the entire thing at once so that all the pieces fit, what you try to do is basically shape every piece so that somehow they will fit together to create the whole ensemble. Right? So it's a very, very difficult approach to build a very complex system. On top of this, there is very little information that is passed across these different models. And one of the reasons is that these interfaces are built by humans for humans. Right, so humans, we can only really handle a few variables, for example, vehicle state, as well as maybe some notion of uncertainty. Right, so every time that we make a mistake along the way, these mistakes are going to propagate, are going to cascade, and there is no hope to really recover from them. And you can think of it as you have to go more and more complex in the decision-making process of the self-driving car. We go more and more blind, meaning that it's really the opposite of what you would like. On top of this, typically what you will see is people having a fleet of vehicles going on the road, capturing these engagements, or where the vehicle actually fails, and then basically categorizing those failures by topics. And then in order to solve every topic, instead of making fundamental changes to the software stack, they basically yet add one more module. And this is the reason why you typically see these overly complicated software stacks with these hundreds of modules inside. For example, your vehicle gets confused about now that it's a fall with the leaves on the ground, so you build a leaf classifier. or bike rack classifier, because there's too many bikes and just a bike detector cannot do it, right? So you can imagine, that you can go exponential in terms of the number of models if you go this way. And what is even worse than this is that there is, when you think about tuning the system, it's really manual tuning, meaning that, you're gonna go and every time that you make a change, it's gonna influence everything else that comes later. So you go one model at a time, and basically you adjust the parameters such that somehow you get good model level metrics at that point. And that's something that, takes a very, very long time. Typically landing a change in production in the industry these days takes 1 to 2 quarters, which is the reason why it has really also asymptote. So we need something different. People have looked at, can we use AI in order to provide us this automation, a way to directly just solve the problem? So the idea is that you have maps and sensors as input, and then you're going to have a neural net that basically is going to estimate all the variables for driving, whether it's steering command, acceleration, etc. Okay. The problem with this is that this approach lacks interpretability and is actually really difficult to make progress, right? Because if something goes wrong, right, the question is, how do you know what to do, right? With a black box approach, it's really, really difficult to, as I said, make progress. And on top of this, you're gonna need, a very, very large number of examples in order to learn from, this type of approach. And in particular, you need to see examples of, for example, safety critical cases, which are unethical to collect in the real world. All right, so what we've been, looking at Waabi, and we build, this sort of idea over the past couple of years before founding the company, is an approach that has advantages of these two kind of lines of work, but without inheriting their disadvantages, right? So the idea is that you're going to have a modular approach where you're still going to be, able to have, interpretability across these models. You can utilize your prior knowledge, but at the same time, it's going to be a single AI stack, meaning that you can train it end to end. Okay, and end-to-end does not mean black box. And that's something that is really a misunderstanding in both the industry as well as academia. All right, so it's going to be an AI first approach, as I mentioned, so a single AI system, end-to-end trainable. And what this gives you is not just the ability to really have automation, but also it gives you the fact that you can now learn much more complex functions, have much more complex interfaces. You can actually, your motion planner can access directly sensor data, etc. So this results in an approach that, has much less problems. It doesn't have this issue of cascading of errors, can actually learn much complex concepts without you explicitly stating, I want my lift classifier or I want my bike rack classifier, right? And you get interpretability, which, as we all know, is important for verification and safety. Now, the particular sort of generation of algorithms that we use for this is instances of what we call deep structure models. So it's very scalable, actually generalizes really well across sensor configurations, geographies, etc. And it's also very affordable because this kind of software stack you can develop with a much smaller team that you typically will develop, this overly complicated industry software stack. Okay, and the last bit that you need when you want to build autonomy is also, a closed loop simulator that actually has like super high level of fidelity that you can test the entire software stack in a reactive manner in closed loop, as if it was playing in a video game. Okay, so that's the other sort of like big component that is required for autonomy in order to both test as well as when you have an end-to-end trainable system. The good news is that you can actually train in simulator as well. Okay, so today I'm going to be talking about autonomy. I will not be talking about simulation, but is one of the, sort of is as important as autonomy, and in the industry hasn't had as much prime time as it should. All right, so I have a very, very ambitious agenda. I want to show you today 3 different types of neural motion planners, and I want to sort of like build chronologically. I'm going to skip a couple that we did along the way, okay? And since I don't have, time to give you, the complete set, but I think this is a pretty nice, subset that will give you sort of an understanding of the kind of design choices that we had and why, why the actual technology evolved the way it did. Okay, so let's go into, the first neural motion planner that we built, which is what we call NMP, right? It was the first interpretable neural motion planner of its kind. All right, and the idea was actually pretty simple, which is rooted on the fact that, as is the topic of this workshop, right? If you think about self-driving, it's really a multitask problem, right? The end goal, yes, is to drive, but along the way, you also want to detect objects. You want to estimate where they are, predict how they're going to be moving, etc. Right? So you have all these different tasks that actually not only give you interpretability, but also helps you to generalize better and learn better. Okay, so this first neural motion planner, we're going to actually just frame it as a straight up simple multitask learning problem. Okay, and the idea is that we're going to have, in this case, LiDAR sweeps. We're going to have maps as well. You can use cameras, all sort of other sensors, right? The same idea applies. And basically, we're going to process the sensor data and the maps through a neural network that is going to give us some really nice spatial-temporal feature maps. And then from this, we are going to have a branch that basically detects, a branch that for the detections regress into the future, the trajectory of the different actors, and a branch that is going to be producing what we call a planning cost volume. Okay, and the idea of this planning cost volume is actually pretty intuitive, which is think of it as what is the price I should pay as a self-driving vehicle to be in every point in a space at every point in time into the future. Okay, so it's a three-dimensional tensor that has 2 dimensions for a space, is bird's eye view, and the third dimension is time into the future, time horizon of your planning, okay, with the plan that you're trying to estimate. All right, then this is basically, you can get this, yes, through a neural network, right? So it's fully non-parametric. And then the question is, how can we use this cost volume in order to plan a trajectory? Very simply, the way that we do this is that we're going to sample a very large number of trajectories. Typically, you do this for a couple of thousands, 10,000 trajectories. And basically, for every trajectory, you can estimate its cost by just indexing this volume. So basically, you just retrieve the specific places in the tensor that are for the specific points in the trajectory, right, going into the future. And then you retrieve those, you sum them, and then that's the cost of a single trajectory. You do this for every trajectory that you have sampled, and then basically you pick with the minimum cost. Okay, so a very, very intuitive, simple idea. And the good news here is that, how do you make sure that things are physically realizable is that your sampler basically already only samples trajectories that you can actually execute. Okay, that's a simple way to get constraints into this type of approach. All right, so this is a fairly fairly simple way to actually do neural motion planner. Now you can instead of using this cost volume, you can use regression, but that works much worse than having a cost volume. And cost volume really gives you interpretability of your decision making as well, as we will see in the video later. All right, so the other thing that is great here is that you can actually train this end-to-end. And the way that you do this is, we have a detection loss, your favorites, a prediction loss, as well as in terms of the motion planner, we cannot just directly supervise the cost volume because we don't know it a priori, right? The only thing that we have is, trajectories of experts. So what we do is basically we use a max margin objective, where basically we say that, we should be close to the expert, and if we are not, we should pay by what is called the task loss. Okay, so this is something that we can propagate back the gradients, right? And basically learn the model in a supervised fashion. All right, so let me show you a video of how well this actually works. So what you're gonna see here is the map that we use, the LiDAR sweep, the detections, the predictions into the future. And the other thing that you're going to see here is in color, you will see some projecting the 3D volume into 2D. And color is the time dimension. And I'm only going to show you areas of very low cost, okay, so that you kind of get a sense without overwhelming you with the visualization of what the self-driving vehicle is thinking. Okay, so here it says that, oh, maybe I change lanes and I queue behind a car, right? Maybe I take a turn or I continue straight. It understands complex notions like, somebody cutting into our lane, right? And sort of prepares maneuvers of potentially changing lanes, as you see over here. It can do nudges as well as super nudges that are, going on the opposite direction. Yes, because somebody is actually blocking the lane, which are very complex maneuvers actually for planners to do. Okay, so this was actually a very simple idea, but it worked remarkably well. Now there's a few, this was done, I guess we presented a CVPR 2 years ago. This work that we started, over 3.5 years ago, something like this, right? So we actually evolved quite a lot since then. And some of the issues of NMP were that the architecture is such that condition on the features, the different branches are independent, right? And this is not necessarily something that we like, because it can lead, even if you use shallow decoders, it can lead to perception or prediction or motion planning to actually have disagreements into what the scene is showing. Something that I want to talk about now is not necessarily just about NMP, but we see in the, in general in the industry and in academia, that when people are looking at this motion planners, or in general, autonomy for self-driving, they use detection-based approaches. And there is really a problem with detection-based that I want to make sure that I highlight today, which is the following. So imagine the following scene. We have the SDV here in the bottom, and we have a couple of objects, a couple of, in this case, vehicles, right, in the scene. So if we are able to detect them all, right, and understand sort of how they're going to sort of move in the next few seconds, then we can actually come up with a pretty decent trajectory right into what to do, and then we will drive safely. However, with detection, what happens is that you only pass to the next stage detections that are above a threshold, right? Or otherwise you will have too many detections, right? So it might be that, imagine the case where there is, for whatever reason, little evidence about this vehicle, and then suddenly you don't detect it, right? So if this is the only information that you continue passing, then what happens is that, well, for the self-driving vehicle, there is nothing there. So it's gonna maybe decide to accelerate to make the turn, and this is gonna lead to a collision. Okay, so having approaches that only rely on detection is actually not safe. Okay, so what typically in the industry, what they do is they have somehow an additional path that takes care of all of their stuff and whatnot, and then there is some heuristics to come up with how do I merge what the detector thinks with what this safety failure kind of path thinks, right? And every time that we have heuristic in self-driving, is actually pretty problematic, because we have little evidence, we make safety critical decisions, and we actually might merge this in the wrong way. All right, so let's look at a different way to actually be able to create perception for self-driving in a way that actually we take into account all objects regardless of how likely they are, so that we don't have this implicit thresholding or explicit thresholding, sorry. So the idea is going to be also pretty intuitive, right? Is we're going to have again our voxelized layer, we're going to have our maps, and now instead of producing predictions and trajectories into the future, what we're going to do is we're going to produce a semantic occupancy field at the current timestamp, as well as future timestamps into the future. Okay, so this is going to be, you can think of it as a tensor, right, where it's going to be spatial as well as temporal, where temporal is the prediction horizon. And on top of this, we have actually we have multiple of these volumes that capture like different semantics that you might be interested in capturing with respect to the different types of objects, right? Whether it's pedestrians or vehicles, cyclists, etc. Also, you can go deeper in the level of semantics. For example, you can have divide the semantics into who is oncoming traffic, who is parked, where there are occlusions, whether someone is doing something strange, etc., etc., etc. Okay, so it's a very you can build actually pretty sophisticated representations this way. Okay, And what is interesting and important here is that vehicles, pedestrians, cyclists, this can actually overlap in the space. A person can ride a bike can be on top of a vehicle, a person can enter a vehicle, etc. Okay? So this is why they are not mutually exclusive. And in particular, the way that we actually estimate those is by exploiting a recurrent network, which is very natural for this. And the reason to use a recurrent net is because we want the occupancy in the future at time t to be fairly consistent with the occupancy at t+1, and this is well captured with a recurrent network. Okay, so again, we have the voxel isolator, we have the raster maps, we have a slightly different architecture in this case in order to first produce some intermediate features and then fuse them. And then basically get the recurrent network that, as I mentioned, basically one step at a time enrolls these occupancies into your prediction into the future. Okay, so this is single observations of the past history, multiple observations into the future of how this future is going to unroll. All right. So the other thing that is interesting with these occupancies is that naturally handles multimodality, which is super, super important for self-driving. All right, so now that we have these occupancies, right, the question is, how can we use this for motion planning? Now, in MMP, right, we use a fully non-parametric motion planner, meaning that, we actually, learn that cost volume, and then basically we use a sampler-based planning that acts at that cost volume, right? And the problem of this is that so although we have things like rules of traffic, collision, etc., as our test loss in the mass margin objective, the model itself was not forced to respect certain things. And when you are really out of distribution, this might lead to not respecting rules of traffic, for example, or even to get into collisions. Okay, so what we're going to do next is we're going to change also the motion planner. It's still going to be a sample-based motion planner, but we're going to use a combination of costs that are sort of built on top of human intuition and many decades of motion planning, and we're going to have some costs that are based on more like learn features. Okay, but the idea is the same. We're going to sample a very wide range of trajectories, and then the way that we sample is actually behavioral, sort of understands behaviors. For example, right, we will have a set of samples for keeping lane, right turn, left turn, emergency braking, etc. Right, and basically we're going to cost all these trajectories and get the one with minimum cost. Okay, and the question is, how do we cost these trajectories? And hopefully this works. Cool. So when so if you think about the things that we have, right? So we're going to build a linear combination of these costs. Which are nonlinear in terms of the input. Okay, so these are nonlinear functions. That's very, very important, particularly since we train them end to end. And we have things like we should avoid occupied regions, right? Using our basically semantic occupancies. We should drive comfortably. We should follow the route. We should drive, close to the center line if possible, because it's safer, etc., etc. Okay, so we have all these different costs. And basically given for every trajectory, we evaluate the costs and we pick the one with the minimum cost. And that's basically the planner. Okay, so we can train this again end-to-end from raw sensor data all the way to the decision making. And the way we do this is that for the semantic occupancy, we can use cross entropy loss using the ground truth occupancy that we can build just with the same types of labels as we would train any perception and prediction system or the neural motion planner before. So there is no requirement to do anything different. And we have the prediction occupancy, and then basically we sort of want them to match, right? So very natural. And then we have a max margin loss that basically says again that we should be close to what the expert driver basically does in these situations. And we should sort of penalize from our best trajectory, the output of the motion planner, from deviating from this through a test loss as well. Okay, cool. So it turns out that this technique actually works very, very well. So what I'm showing you here is different types of motion planners, from behavioral cloning. That would be the typical thing you will see. More simple planners that you use, you will see more in the industry, like adaptive cruise control. You also respect the neural motion planner, and this is sort of like multipath followed by a sophisticated planner. And P3 is actually our end-to-end planner. Okay, so you see that. So we make as much progress as any other approach. We have less jerk. We have as good in terms of the imitation learning as the behavioral cloner, right? Which is the only objective that it learns, right? So that's actually pretty good, and it's much safer in terms of collisions. In this case, it's open loop, meaning that you have the past, and then you want to predict your trajectory, and then you evaluate the entire trajectory into the future. Okay. So let me show you some representations of what this technique does, and you're going to see here on different colors, like the different semantics, where you see pedestrians, bicycles, vehicles, and for vehicles we have like different types, as I say, of semantics. For example, whether it's stationary, is driving in our route, is oncoming traffic, etc. And I'm gonna basically show you again open loop trajectories, or sorry, occupancies, which is we have the sensor data up to this point. What is the vehicle thinking that is gonna happen in the next few seconds, and what is in the absence of replanning, what is the trajectory it intends to take? Okay, so let's see how this works. And what you can notice that is very multimodal. You see here, very natural in terms of, we could have continuous straight, or we could have taken a turn, and then, our type of semantics will be different. It also kind of captures the notion of occlusion well, right? Probably there's going to be maybe something parked here, somebody parked here, despite the fact that there is occlusion, and I don't see. And there's also like stationary vehicles along the way, etc. Okay. The other thing that is quite interesting is that, these occupancies are still able to capture like really fine-grained behaviors. For example, it can very naturally sort of predict where pedestrians are going to be going, as you see super accurately, right, crossing sort of in this crosswalk. And it predicts really nicely that this vehicle is sort of stopping or slowing down so that the pedestrians can actually pass. Right, so fairly sophisticated sort of interaction between several actors are naturally captured here. Now, everything that I show you so far is in this case was with open loop evaluation, and the problem with open loop evaluation is that you don't see compound of errors, right? It's that you get a good initial good sort of data, right? You have driven so far, and then tell me how you're going to drive only in the next, say, 5 seconds. Right, so you don't see what happens if I deviate a little bit. Is this going to, result in catastrophe? So we're going to go now into closed loop evaluation. We're going to use a realistic LiDAR simulation for this. So this is, as I mentioned before at the beginning, this is the reason to use simulation, right? That you want to really test the entire software stack. This is what we're going to do here, and the actors of the simulator are actually reactive, meaning that they are intelligent. They will slow down or slam the brakes, etc. And this is sort of like the LiDAR simulation that we do, right? For this closed loop simulator, that will be the input to our autonomy system. Okay, and again, this is very important because we want to test the entire software stack here. All right, so these are sort of metrics in terms of closed loop simulation, and you see much bigger differences with respect to the best, in this case, of all of the techniques is this multipath style plus PLT. And you see here in terms of collision as well as comfort, as well as progress, this end-to-end system with occupancies is way better than anything out there. Okay. All right, so in the last 10 minutes, we're gonna go into the next level, which is, if you look at everything that we have done so far, we have assumed that we have high definition maps of the environment. And this is great if your localization system is perfect, if you have invested millions and millions of dollars on building these maps, but localization might fail, or it doesn't scale super well these days to basically build high definition maps. Typically in the industry, it takes it costs around almost $1,000 per kilometer to build an HD map once, right? Imagine then you need to maintain it, etc. Okay, so what we're gonna do next is we're going to look at, can we use this type of end-to-end motion planner to actually drive without a map? Okay, and we still need to understand the notion of a route, right? So we have a little bit of info, but you can think of this as, mapless driving, very similar to how humans do. Okay, so as I was mentioning before, driving with an HD map, it eases perception, prediction, planning, right? So it's great, but what if localization failed and these scalability issues? And now we're going to look at the only thing that the vehicle receives is this really high level commands, like your GPS will tell you when you drive, turn right at the next intersection, right? Or bear left. Okay, and given just that kind of high level command, you actually need to drive around. So you have no idea where the lanes are, where the crosswalks are, etc., etc. Okay, so this is, we have much more relaxed requirements. It's very scalable, this approach. However, is actually pretty difficult to do, I guess, autonomy when you don't have high definition maps. And if you look at the literature, basically, like in planning, almost everything is targeted to the fact that you have a high definition map in the first place. All right, so let's try to build this approach. So we're gonna have we're gonna start with sort of like similarly as before. We have the observations. In this case, again, LiDAR is reflected here. You can use, again, a combination of sensors. And we're gonna build some semantic representation, given this input. And again, remember, we don't have maps, right? So this is kind of the only thing that we have as input. And in terms of the semantic representation that we build, it's gonna be two types. We're gonna build online maps, right? Because we still need to understand, where we can drive or not, right? But we need to infer this online, right? Just from the raw sensor data. And then we're also gonna use some notion of occupancy, right? That we saw before, that it was, very useful for the dynamic or things that potentially are dynamic in the scene. Okay, and these are the two sources of information that some of the two sources of information that you will need in order to drive. And there is one more bit that we need, which is, I mentioned before, these high level commands, right? Like, for example, keep straight, turn right at the intersection. So we are also going to need to translate this into the route that we need to follow. Okay, so we're going to use the online maps that we have generated with the command. And then through a neural net, we're going to basically transform these two sources of information into the route itself. That looks much more similar to what is a route typically when you have HD maps. And together with the occupancy, we are going to basically compute our costs. And we're going to use a sample-based planner, right? That samples trajectories, utilizes all these sources of information to cost, and then basically picks the trajectory with the minimum cost. Okay, so it's a very, very interesting architecture. And this is, again, something that we're going to be training end-to-end. And again, it's very, very natural. This really looks like something like humans, right? You have your GPS, high level, you have your eyes, and then basically you drive around. All right, so I'm going to give a couple of details on the scene representation and the motion planning, and then I'm going to show you some results. All right. So let's go into the scene representation. So as I mentioned before, in terms of the scene representation, we're going to have both the online maps as well as the occupancies representing the potential dynamic actors, right? And in terms of the maps, so we estimate like 4 different types of things. Drivable area, which is, all the area around the vehicle where you can actually drive. This is important, for example, for maneuvers like, safe stop, etc. We're also gonna sort of estimate what are the reachable lanes. This is in the absence of any route. What are all the options that you have? Okay, this is an intersection, and we have the vehicle can turn left, can continue straight, or can take a route. Okay, we also estimate intersections. This is actually useful for pedestrians. And then, some kind of angular representation that also helps us with, our cost. Okay, and in terms of the semantic features for the dynamic objects or potentially dynamic objects, we are going to change a little bit from before. So if you remember in P3, which was the previous motion planner, we use occupancy through a recurrent net, right? And we estimate at every point in time into the future, right, this occupancy. And one of the things that is still, potentially you still see from time to time in this kind of recurrent representation is that there might be inconsistencies between your predictions into time t and time t+1, t+2, etc. Okay, this is predictions given the same observations, predictions into the future. Okay, so we're gonna make it super explicit through a flow representation, such that we only predict a single occupancy at the first timestamp, and then we have motion fields that transform this occupancy into the future. Okay, then you predict these motion fields for the next timestamp, next timestamp, etc., up to your planning horizon. Okay, so this by definition, by construction, is actually consistent. Okay, yes, so to make sure that everybody's on the same page. So we have, this is a simplified representation here, right? But you predict, this is your baseline view pixelization, right? Voxelization. So you predict what is occupied, and then you predict a motion from time t0 to t+1 to t+2, t+3, etc. Okay, and the way that you will estimate the occupancy here is that the occupancy and the flow, basically you deform the occupancy through the flow, and then you get the next occupancy. Okay, and do the next thing, etc., etc. And again, this is consistent by construction, right? Because you're estimating motion of occupancy that existed in the first place. All right, so this basically will make things, for example, that things do not appear and disappear that might happen when you use a recurrent net. All right, let's look a little bit at how we build the motion planner. So in this case, for the motion planner, there is a couple of bits that we're going to change, right? First is how to handle or how to deal with this routing. So in particular, what we're going to do here is that we're going to do a conditional prediction of the route. So given the type of action that we have, basically you can think of it as we have different weights that basically estimate the route. Okay, so it's pretty simple model, a conditional model, and this actually works pretty well. In terms of the trajectories, we are also going to change. I'm going to use something that is very powerful, which is instead of us generating trajectories with some clotoidals or polynomial functions, instead we're going to use retrieval, which is, we have a whole bunch of data trajectories that were driven, in the different operation domains that we operate. And then basically we're going to retrieve, given the particular steering and velocity and acceleration of the self-driving vehicle, we retrieve from our data set trajectories into the future for sort of the bucket that is close to the steering velocity acceleration that we have right now. Okay, this is some examples for some steering and some velocities given the same kind of acceleration. Okay, and you see here that you have like very, very nice sort of types of trajectories, reflecting map changes, all sorts of things. All right, so given now this new way of sampling, now we need to cost these trajectories. And the way that we do this is the following. So I'm going to show a few of the costs. There is more cost than this, but basically we have, in this case, you don't want to go into occupied regions. You want to stay into what you predicted to be a drivable area. You want to stay close to what your route was. We use the motion, right, as a way to predict sort of like safe headway. This is sort of like SEC kind of behavior. So that's actually important so that we nicely slow down to the car in front of us. We also want to stay close to the reachable lanes and you should drive comfortably, for example. Okay. So very natural cost. And we pick basically the trajectory with the minimum cost. Now you can train this whole thing end to end by using again max margin and cross entropy for the different things, as well as negative log likelihood for the mapping. Okay, so the entire system again can train end to end. How does this work? So we need to build versions of previous approaches without using high definition maps. And what you can see here with M3 is that in this case we're going to flip it. We're going to look at success rate. Okay, so the higher the better. This is the higher the better, this is the lower the better, and this is the lower the better. Okay, so we succeed much more. We stay in the route much more than any other approach. Right, things like behavioral cloning, right, really don't work very well. Look at staying route, right, shoots off all the time. We actually stay close to the human demonstrations, and we are very, very smooth, as you see here. All right, so let me actually, yes, pause this for a second and basically show you. In this case, you're going to have voice over.
As it executes the planned actions, we can see how the plan, shown in blue, diverges from the trajectory the expert performed when the lock was recorded, shown in black. Here, we showcase an interesting scenario where the self-driving vehicle exhibits cautious behavior around fast-moving traffic, similarly to what the expert driver did. In this other scenario, we first highlight the accurate route prediction for a left turn in an atypical map topology. As the other cars pass by, our model shows more cautiousness than the expert driver when yielding to them. At the core of safety in a self-driving vehicle is the behavior around heavily occluded pedestrians. In this example, we can see our model safely predicts a pedestrian in between cars might jaywalk, and we reduce speed accordingly. MP3 can also navigate a heavily crowded five-way intersection with an atypical topology by driving cautiously. Finally, we can see how it yields to pedestrians at the crosswalk. Next, we compare to the baselines one by one in this simple scenario. The self-driving vehicle is supposed to progress along the orange route by following the high-level commands. We first compare against conditional limitation learning, where we can see a clear difference in behavior. This baseline is unsafe and doesn't obey the commands. Next, we compare against trajectory classification. While this baseline behaves better and follows the direction of traffic, it does not respect other traffic participants. Finally, the conditional neural motion planner exhibits very similar behavior to trajectory classification in this example, which is far from the expert in our model.
Good. So that gives you hopefully an understanding of how this method works, and it's like very, very significantly much better than anything else. Great. So to conclude, I show you 3 types of neural motion planners. We went in increases level of difficulty and sophistication of the model. Right. We started with multitask. We went into P3 with some occupancy-based methodology, and then we show how to get a mapless version of neural motion planner. And this mapless version can be, for example, the safety net in case your localization fails. So I want to just conclude by saying that the promise of self-driving is really the promise of a better world, and and it's going to create incredible value for our society. It's going to save many lives. It's going to transform the landscape of our cities, hopefully to become much greener. It's going to enable us to solve some of the supply chain issues that we see right now, where we cannot get the goods that we need. The thing that we need is really the right technology, and current approaches are not solving, are not in the path to solve this at scale. So we need something else. We need self-driving 2.0, and hopefully today I show you and you understood a bit of what the future of self-driving looks like. And we are very excited, heads down, working on this at Waabi. We have plenty of openings, so if you are excited about changing the world, please come and join us. So this is all for me today. Thank you.